Welcome to the Professor's DuBois channel. This is Professor Corey, and this video is a mini lecture based on our third and final lecture covering material from Chapter 7. The lecture begins with a question. When asked which is larger, it is reasonable to think that fluorine would be larger than lithium because it has more electrons. We have stated previously that the size of the atom is determined by the electrons, since the protons and neutrons are contained within a very small nucleus. The electrons are located in orbitals outside of the nucleus, so measuring the atom involves the electrons. The reason that lithium is actually larger is because fluorine has more protons, and the outermost electrons are still in n equals 2. The additional protons have more pull on the electrons and hold them closer than lithium can. You can see the trend of atomic size for the elements. Size increases going down the periodic table, and this makes sense because each period has an additional n level. Within a period, the largest is to the left because all of the electrons are in the same n level, but the left of the period has fewer protons in the nucleus, so the pull on these electrons is less. You may see the letter Z star, and this is called the effective nuclear charge. More protons means a stronger pull, but there are other factors to consider. One is distance. As the electrons are further from the nucleus, the pull is not as strong. In addition to this is the repulsion felt as the result of the other electrons. The negative charge of an electron will repel other objects with negative charges, including electrons. This effect is called screening or shielding, and as the result, a weaker grasp on the outer electrons is felt from the nucleus. Oftentimes, ion size is compared. This is not necessarily a periodic trend unless we're comparing ions within the same group. Let's consider group 1, the alkali metals. The potassium ion would be larger than the lithium ion. More common is to compare an ion to its neutral atom. This can be solved by considering the electrons. Anions have gained electrons and are larger than their corresponding neutral atom. Cations have lost electrons and are smaller than their neutral atom. The most common comparison would be isoelectronic species. This is solved by counting the electrons first. If each has the same number of electrons, meaning isoelectronic, then we look at the number of protons. The atom or ion with the most protons will be the smallest. More protons equals a stronger pull on the electrons. This image shows the atom and ion sizes for both cations and anions. Ionization energy is the energy required to remove an electron. Metals like to lose electrons. This is the quickest path to a noble gas configuration, so it is logical that the ionization energy would be low, and this is true. Fluorine has a very high ionization energy since it only needs to gain one electron to have a noble gas notation. In addition, fluorine's electrons are in n equals 2, which is relatively close to the nucleus, so the pull is rather strong. We can represent this trend as increasing as we move from the bottom to the top of the table within a group, or if we move left to right along a period. Fluorine's ionization energy is very high, while francium has a very low ionization energy. We can have several ionization energies for an atom, and each requires more energy. When an atom reaches noble gas configuration, the ionization energy becomes extremely high because at this point the atom does not want to lose or gain any electrons. This slide shows some actual values of ionization energies. The large jump in energy between the second and third ionization energy for beryllium is due to reaching a noble gas configuration. Lithium is in group 1, so it makes sense that the second ionization energy would be much greater than the first. Electron affinity is a measure of how much an atom wants an electron. It is logical that fluorine has a large electron affinity and francium has a low electron affinity. The trend is the same as for ionization energy. We can use diagonal arrows to represent the trends, and so far we have ionization energy and electron affinity trending in the same direction with an opposite trend observed for the atomic radius or the size of the atom. Electronegativity is very similar to electron affinity and scales from near 0 to 4.0, with fluorine holding the highest electronegativity value of 4.0. This is the same trend as ionization energy and electron affinity. This table includes electronegativity values for the elements. Notice that the trend is higher in the upper right, but also realize that the trend is not perfect. Tungsten, for example, has a high value of 2.4 and is located near the bottom left. A list of electronegativity values is typically provided for an exam, but if not, you can use the trend to answer any problems regarding electronegativity. The final periodic trend that we will discuss is metallic character. Since the metals are on the left of the periodic table, it makes sense that the trend would increase from right to left, and this is true. Francium has more metallic character based on the idea that metals lose electrons. Although francium has a lot of protons in the nucleus, the effective nuclear charge on the outermost electron will not be very strong due to shielding and distance, so this electron can be lost easily. The trend is the same as atomic radius. We have discussed 5 periodic trends in this lecture, as well as some ionic comparisons. Your assignment is to be able to explain these, as well as to answer related questions prior to the next lecture. Thanks for watching. Please give the video a thumbs up and subscribe if you would like to see more mini lectures on the Professor's DuBois channel.